Hey there, welcome to Bright Engineering. Today we are going to look at star delta connection. So we are going to look at an instance where we consider resistors to be in star or delta and then how to convert from one to the other, right? So first of all, let's briefly look at series and in parallel connections, right? So we saw that resistors are in series if the same amount of current flows through them, right? So it means that if you have these two resistors in series, if you have one R1 and an R2 that are on the same line, and then there is a current here that is being produced, say I, this I is going to pass through this R1, and it's the same thing that's going to pass through R2, right? So it means that these two resistors now become resistors in series because the same amount of current is passing through them, right? Now we say that resistors are also in parallel when you can move through them, when it share two common nodes, and then you can move through them without missing any other branch, right? So when we have a circuit like this, where this voltage source can produce a current I, and then this two resistors, which is R1 and then R2, you can navigate through them without meeting any other branch, but then instead they share two common nodes. So it means that if you consider these two, they share this common node, right? Because there is no element here, this is the same as drawing it as this. Right? And then that same way we can also do here the same, so it can be like this, like it connects here, right? Because there's no other element. So when they share these two common nodes, 1 and then 2, without meeting any other branch where you can just navigate through them like that, then it means that those two elements are in parallel, right? So an instance where you have a circuit and then those elements in that particular circuit, when you navigate through them, current cannot flow through them easily, or the same amount of current does not flow through them, and then also they don't share two common nodes where you can just navigate through them. It means that they are not in either series or parallel, right? And if they are not in series or parallel, then it means that we are now considering star delta. Now when we are talking about star connected or star connection, we say that resistors are in star connection when they have a common point, right? So when you have three resistors, say R1, R2, and then R3, and then they share a common point, we see that these three resistors are in star connection, sorry, because when you take these two, the same amount of current will not flow through this, because if current is to apply to this part of the circuit and then it gets here, current would have to split here and then here, right? So it means that not the same amount of current will not flow through this and this. And then when we are talking about parallel connections too, we see that these two are not parallel, right? Because you cannot navigate through them without meeting any other elements, right? They don't share any two common nodes, right? And then these three has just a common point, so we call this star connection or Y connection, right? Now let's look at delta. So when you have three different elements that the starting point of one is connected to the tip of one, and then the end of the another is connected to the tip of the other, we say that those three elements are delta connected, right? So with this, it means that obviously when current or when a voltage source is applied to it, we can't say this and this are in series, right? Because here is a node and on this side is a node. When current gets here, the current would have to split here and then here, right? And at the same time, when it gets here, it has to split here and then go backwards, right? And then the reason why, even though current is splitting, but then these two are not in parallel, is because they share this common node, which is 1, but then when you are navigating through them so that you can see if they share a second node, it's not possible because there is this element there, right? So it means when you pass here and then you get to this node, when you're moving through here and then you are going to this node, you see a different element, so they cease to be in what do you call it? They cease to be in parallel, right? So that's the idea about star and then delta connections, right? But then if you have a star connection and you want to change to delta, or a delta connection when you want to change to star, how do you go about it, right? So now let's draw a circuit with both elements. Alright, so sorry for the way I'm drawing my diagram, okay? Don't worry, you will be fine. So we have R1, R2, R3. So from what we explained earlier, because these three, the end of one is connected to the tip of one, and then so these three are in delta connection, right? So R1, R2, and then R3 are delta connected, right? In that same way, because these three are also sharing a common point, we can say that those three is star connected, right? So we can say we have RA here, we have RB here, and then let's make it this RC, right? So from star to delta, if we want to change from star to delta, right, now we are considering this. So this is our star. So what if we have values here and then we want to change it from these values to get R1, R2, and then R3, right? So let's first find R1. So if you want to find R1, we are saying that from star to delta, you consider the addition of the multiplication of two of them each, right? We just call it sum of products, SOP, sum of products, right? So when you take R1, you have to multiply RC by RA, RA by RB, and then RB by RC, right? So when you add them up, then you divide it by the resistor that is opposite to what you are finding, right? So when we look at this star connection, the RB is opposite to the R1, which we are finding, right? So after we found the addition of the multiplication, then we have to divide it by this single element, right? So to find R1, we are getting RB plus RC plus RC, all divided by what is opposite to the R1, which is RB, right? So R2 is also equal to the same thing, but then we divide by the one that is opposite to it. So one common thing that you can keep in mind is that when you are changing from star to delta, they all have the same numerators, right? So you can just keep that in mind and then take it wherever you go. And no matter what happens, if you are changing from star to delta, the numerators are always the same. So we don't have to stress ourselves and go through the diagram again, but then we can just maintain our numerators, RC plus RC, right? But then we are going to divide by the elements that is opposite to the R2. So when you take R2, it's RA that is opposite to R2, right? So we get divided by RA, right? And in that same way, when we are changing, we are finding R3, we maintain our numerator, and then we divide it by the element that is opposite to R3, which is the RC, right? And then this is how we convert from star to delta, right? So we are going to look at an example of converting from star to delta, and then after that we look at a complete circuit, right? So now let's look at how you can be able to change from delta to star. All right, so this is from our star to delta. Now let's consider from delta to star. So the delta is the outer element, right? And we want to convert and find what is inside here. So when we take this particular element, which is the RA, and then we want to find RA, right? We are saying that the numerator is just the multiplication of the two elements in which the RA finds itself, right? Then you divide it by the sum of the other elements. So to find RA, it's equal to the two elements that it finds itself in, which is the R1 and then R3. So R1 times R3 divided by the addition of the three elements, so R1 plus R2 plus R3, right? And the same thing applies to RB. Now you find the one that it's in between, which is the R3 and then the R2, right? So you're getting R2, R3 divided by the sum of the three. So when you consider these two, you can see that always the denominators does not change, right? So R1 plus R2 plus R3, and then here for RC we are getting R1 and R2 because it's in between R1 and then R2, right? So when you are changing from star to delta, the numerator does not change, and when you are changing from delta to star, the denominator does not change, right? So please keep this in mind, and then we are going to use it in our calculations very soon, right? So let's just consider a single diagram of, say, let's give here 2 ohms, 2 ohms, right? And let's convert this star to delta, right? So it means that if you have to convert this star to delta, if you have to create our delta diagram here, and name it. So maybe RA, RB, and then RC, right? And you know that from star to delta, obviously our RA is going to be the SOP, that's the sum of the products, which is this by this plus this by this plus this by this, right? So we are getting 2 times 2 plus 2 times 2 plus 2 times 2, right? Divided by the elements in which it finds itself in, which is this 2, right? So we are going to get 4 plus 4 plus 4, which is going to give us 12 divided by 2, and then our answer is going to be 6, right? And since all the elements here, the values we have here is 2, it means that we are going to get the same value for RB and then RC2, right? So it means that RB is going to be 6, RC is also going to be 6, right? So the same way, if we have to change from delta to star, say here is 2 ohms, here is 2 ohms, and here is 2 ohms. You have to change to this star, so say R1, R2, and then R3. To find R1, we know that it is the multiplication of the 2 elements which it finds itself inside, which is these 2. So 2 times 2 divided by the addition of the 3, so 2 plus 2 plus 2, right? Which is going to give us 4 divided by 6, right? And when we have to divide this, we are going to get 0.66, right? Since the elements are the same, we are going to get the same for R2, which is 2 by 2 over 2 plus 2 plus 2, 4 over 6, and also going to be 0.66. And then R3 is equally going to give us 0.66, right? So looking at the question like this, where we have to find the current flowing through the 30 ohms resistor, the first thing that we have to do is that, of course, we have to find an equivalent resistance for it so that we can find the total current that is flowing through the circuit, right? So in this case, we would, because we want to reduce the resistances, we would find if there are any other resistance that are in series or in parallel so that we can reduce it quickly, right? When we take this and this, they are not in series because, of course, there is a node here, so there's going to be a split in current, right? And they are also not in parallel because even though they share this common node, they don't share a different node again because of this particular element, right? So we take this and this are not in series because there's going to be a split because of the node, and they don't share 2 common nodes, so it means that they are neither in parallel to because of this particular resistance, right? So it means that all the elements that we have here are neither in series nor in parallel, right? So what we are going to do is that we are going to find the best way out possible. And if you are looking at it, like we said that for elements to be star connected, they have to share a common node. So when we look at these 3, 1, 2, 3, they share this common node, right? So it means that it is star connected. I hope you understand that. Good. And then when we take these 3 to 1, 2, 3, it's delta connected, right? Because the tip of the other is connected to the end of one, this tip is connected to the end of it, and then this tip is also connected to the end, right? So these 3 elements is delta connected. The same thing applies to this one because this 3 element is also delta connected. And when you take these 3 to, this tip is connected to this tip is connected to this here, and this tip is also connected to this here, right? So it means that this is also delta connected, right? So now we can choose to convert any way possible that we want, either change this to star, this to star, this to star, or the middle one to delta, right? So let's start by changing this middle one to delta connection and see how our circuit is going to look like, right? So if we are to change this to delta connection, then we are going to get rid of these three elements, right? So our equivalent circuit is going to look like this. All right, so our equivalent circuit is going to look like this because our data is going to be this way, and of course we are going to get one here, which is this one. But then we don't know the values of these resistors, right? So we are going to assign to them R1, R2, and then say R3, right? So it means that if you have to find, to make it look simpler for us, let's just bring short dashes here. Right, so we know where our R1 is, and then where our R2 and then our R3 is, right? Good. All right, so we have our R1, our R2, and then our R3, right? And looking at the short dashes, here is going to be R1. So changing from star to delta, we said that always from star to delta, the numerators are the same, right? And the denominators are just the one that is opposite to what we are finding, right? So for R1, which is this side, it is this 5 times 10 plus 5 times 20 plus 10 times 20, right? So we are going to get R1 to be equal to 5 times 10 plus 5 times 20 plus 20 times 10, right? Divided by the one that is opposite to this, which is the 20, right? So divided by 20. So we are going to get 350 divided by 20, and then our answer is going to be 17.5 ohms, right? So now that we know that this total is 350, we didn't waste our time with the rest of them, right? So R2 is just 350 divided by, so looking at R2, which is here, the one that is opposite to R2 is this 5, right? So 350 divided by 5, and then our answer is going to be 70 ohms, right? And then R3 is just 350 divided by 10, and our answer is equal to 35 ohms, right? Good. So now we know that R3 here is 35, R1 here is 17.5, and R2 here is 70. So when we have something like this, now we can reduce it because we know that this and this are in parallel, right? They share this node. We can move through this to get to this node, pass here, move through this, and get to this node without any other element. So it makes these two in parallel. Same thing applies to R3 and then 15 ohms, right? You share this common node, you can move through here, and then they share this common node. Same thing applies here, right? So in order to find that, we can find the 12.5 is parallel to R1, and R1 is 17.5, right? And then our answer is going to be 12.5 times 17.5 all over 12.5 plus 17.5, right? Then it's going to give us 7.29 ohms, right? That same way, we can also find for the 30 and then the 70, right? So we know that 30 is parallel to 70. Getting 30 times 70 over 30 plus 70, right? And our answer is going to give us 21 ohms. And then we can find the last one, which is 15 parallel to 35. 15 times 35 over 15 plus 35. Then we are going to get 10.5 ohms, right? So now that we know the equivalence, now we can also draw another equivalent circuit for it. So someone will ask, is it important to be drawing this circuit always? The answer to that is that to make your to make your work look simpler so that you don't confuse yourself or you don't get confused along the way, I would advise you draw them. But then if you think that you can work your way through it without drawing these equivalent circuit, then you are also good to go, right? So the equivalence of these two, we have 21, right? So here is 21 ohms instead. The equivalence of these two, we had 7.29, and the equivalence of these two, we had 10.5. Not forgetting our 120 volts. So now we can see that these two are now in series, because when current is to flow through this particular resistor, the same amount of current will flow through the two, right? So now that we have these two in series, then we can add them up to get our 7.29 plus 10.5, which is our 17.79, right? So these two are in series. Now we can also find this and this equivalence by using parallel circuits, right? So now 17 is parallel to 21. Now answer is 17.79 times 21 over 17.79 plus 21, right? And we are getting 9.63 ohms, right? So the total resistance of this is 9.63 ohms. So if we have our equivalent resistance, then it means that we can now find the total current that is flowing through the circuit, right? And from Ohm's law, we know that I is V over R. So our current is just the voltage, which is the total voltage 120 divided by the total impedance, which is 9.63. And now our total current is going to give us 12.46 amps. Sorry. But then the question is, find the current flowing through the 30 ohms resistor. So we are interested in the current that is flowing through this 30 ohms, right? Good. So now that we have our 12.46, now we will be working backwards with this circuit and now with this circuit. Please, I hope you get it, right? So when we get this circuit, now we know that when current is flowing through here and then I is 12.6 and it gets here, it's going to split, pass here and then pass here, right? So now we can use our current divider rule to find the current that is flowing through this 21 ohms, right? And like we discussed earlier, we said that when you want to use current divider rule to find the current that is flowing through one part of the circuit, the one that has to be the numerator is the other one, right? So it means that our 17.79 is rather going to be the numerator, right? So current through 21 ohms is going to be the 17.79 divided by 17.79 plus the 21 times the total current, which is the 12.46 amps, right? And then this, we are getting 5.7 amps. So now we know that 5.7 amps is flowing through this 21, but originally this circuit or this resistor wasn't 21, right? It was just a parallel conversion or equivalence that gave us 21. It means that we have to go back to the circuit and see how we can get through to the 30, right? So if you come here, we know that it was the equivalence of this R2 and this 30 that gave us 21, right? So it means that when current gets here too, between this and that, it has to split, right? It has to come here and it has to go here. And now we are not interested in the current flowing through the R2, but we are interested in the one flowing through the R3. So in that same regard, we are going to use our current divider rule, this divided by the addition of these two times the current that is going to split, right? So now we are going to get the current through the 30 ohms resistor. And now our answer is going to be R2, which is the 70 divided by the 70 plus 30 times the total current that is flowing through the 21, that's both of them, which is the 5.7 amps, right? And now our answer is going to be 3.99 amps, right? So when you have something like this, then it means that we can now find the current flowing through every element in that particular circuit, right? So thank you for following us, and if this video has been helpful, please don't forget to subscribe, share, comment, and then like.